afternoon. We're going to get started. We have a lot to cover today. By the way, I made the sapling deadline Saturday, and the reason I did that is because there's an extra practice sapling that's not worth any points that I'm going to open up early Sunday morning that has synthesis from all of the sapling chapters mixed together. So I couldn't have the deadline be Sunday, so that's why it's an early deadline for a sapling. Are there any questions before we get started? Anybody? All right. Okay, so we're going to be synthesizing more complicated things than we've seen so far in chapter 18. And the key thing to know about this is that these are the things that we can do in one step on benzene. R meaning just some sort of alkyl group. If you want to put something more complicated on the benzene ring, you need to put a simple thing on and then change the simple thing to something more complicated. So there's this tendency for students to, if I have this really complicated thing hanging off the benzene ring, slap a chlorine on there, throw it in with AlCl3 and expect it to go on the benzene ring and do what you want. That's not the case. We know how to put a sulfonyl group, we know how to put a nitro group, we know how to put an acyl group, we know how to put a simple alkyl group. We know how to put a bromine. Those are the only things that we know how to put directly on the benzene ring. If you want to put something on more complicated, you have to put one of these simple things on and then change it to something else. So this is where all of the chemistry that we've already talked about this year comes in. So we're just going to use, we're going to use the reactions from chapter 7, chapter 8, 9, 10, 11, 12, 15, 16 to now convert those functional groups into what we want. All right, so here's some examples here. And so a lot of people ask me, is the final going to be mostly on new stuff? Absolutely not. The first midterm was on 4 weeks. The second midterm was on 4 weeks. I'm not going to have a midterm that's worth, I'm not going to have a test that's worth double on 2 weeks of material. You would not want to take that test. It would have a very low mean, okay? So you don't want to do that. And I don't even have to try to make it cumulative because you put on something simple on the benzene ring and then you use other reactions, it's going to be cumulative. All right, so for example, we can put a methyl on a benzene ring and then we can use chapter 15 material. Turn that into a bromide, put a functional group on, then we can treat that with an alkyne, and then we can take alkynes and we can convert them into ketones, aldehydes. You know how to do that. We could also do SN2 reactions here, so this would be chapter 7, N3 minus, cyanide, that's also chapter 7. And then, or we could put an OH and then we could oxidize that, so simple substitution reactions from chapter 7, and then this would be chapter 12. To oxidize that. KMNO4 turns that into a carboxylic acid. That's on the next page. So we haven't talked about that reaction yet, but that's something else that you can do. In other words, what you're not going to be able to do is put this group on directly by just throwing a chlorine on this and then adding AlCl3. So that's sort of the take-home message here. You're going to have to do these more complicated ways. All right, here's some more examples of things that we can do. We could use NBS, peroxide, heat or light. We can put a bromine on there. We can eliminate. And then now we can do all the reactions from chapter 10. We could convert that into an alkyne. You should be able to fill in all of these things. Or we could do any of the chapter 10 reactions. So hopefully you're getting the idea that the synthesis on this final is going to be very cumulative without me even trying to make it cumulative. So those are all reactions that you know, except for potassium permanganate. I'm going to talk about that right now. And there's a couple of new reactions in this chapter that we use to make changes on groups that are bonded to a benzene. All right, so this first one is oxidation of alkyl groups bonded to aromatic rings. We use a familiar reagent for you, potassium permanganate, heat, sodium hydroxide. The heat is key here. We've used potassium permanganate in chapter 12 to make a 1,2-diol, right? And I always wrote cold because that reaction is done at a low temperature. If you heat this up, it's a very strong oxidizing agent, and it does a much more vigorous reaction. So that's the difference here. The heat versus the chapter 12 of KMNO4 reaction is low temp. All right, so what happens is if you have, it doesn't matter what this alkyl group is, as long as there is a benzylic hydrogen, all of these have a benzylic hydrogen. So must have benzylic hydrogen. It does not matter how long the chain is, as long as there's a benzylic hydrogen. It can be a methyl, it can have one benzylic hydrogen, it can have two benzylic hydrogens or three, does not matter. No matter how long that chain is, you're going to convert all of these into a carboxylic acid. So the potassium permanganate is going to just basically chew up that ring. It's going to turn it into mostly carbon dioxide, and then you're going to get, and it stops right when you get to the benzene ring. Again, so no matter how long that chain is. If you have something here, this has no benzylic hydrogen. And so therefore, no reaction. Have to have a benzylic hydrogen for this to work. So that's good because now that's a way that we can put an acid, a carboxylic acid, directly onto a benzene ring. Hadn't learned how to do that before. All right, so comparing that with this one, see the difference? Here's to high temp. This is low temperature. If you used high temperature for this reaction from chapter 12, it would chew up this molecule also and turn it into carbon dioxide. So the temperature is key here. All right, so that's a new reaction. There's a couple more new reactions. And this is going to, as you see, we've just expanded the number of things we can put on a benzene ring. This also we can too. A nitro substituent can be reduced using catalytic hydrogenation or by using metal, tin, iron, or zinc plus hydrochloric acid. The product is aniline. This is the one that I use. I don't usually use tin for that reaction, although you might see it in your book. You might see it on sapling. I use zinc. And so what you get here for both of these, H2 palladium reduces this to an NH2. So now we have a way to make aniline that we didn't have before. Zinc and mercury amalgam and hydrochloric acid, you're going to make aniline also, but since you're in acid, it will be protonated. So if you use this method to make aniline, you have to add an extra base. So what we would call is a basic workup. So two new ways to make aniline that will be very useful in synthesis. Another reaction is the Clemmensen or the Wolff-Kishner reduction. And I'm not going to ask you mechanisms for either of these, but what these two reactions do, and so we have that previous one, we have this one, so this is 4 new reactions in this chapter besides the electrophilic aromatic substitution. And in this reaction, Clemmensen or Wolff-Kishner, you replace a carbonyl with 2 hydrogens. And note that that's not the same thing that hydrogen and palladium does. Hydrogen and palladium will reduce that to an alcohol. But if you want to take and replace that oxygen with 2 hydrogens, this is a reduction reaction. You need to use Clemmensen or Wolff-Kishner. If you do this with this substrate here, it's going to reduce the ketone only. And I don't know why I'm drawing that when I'm saying it's going to be reduced. CH2, CH2, CH2. So the carboxylic acid is not touched. So let's write down what we just added. We did this, a hydrogen here, carboxylic acid not reduced. So these reagents reduce Clemmensen or Wolff-Kishner, ketone and aldehydes only. Oh my gosh, why did I do that again? Okay. Let's just write it down here. Ketones and aldehydes only. So Clemmensen Wolff-Kishner reduces ketones and aldehydes only. That's why when nothing happens to the carboxylic acid. So zinc mercury amalgam does that, and Wolff-Kishner does the same thing. And that also only works for ketones and aldehydes, not carboxylic acids, not esters, not amides, not acid chlorides. All right, so just keep in mind that, let's go back here. I got those both on the screen. This is the same thing. So that means that if you have let's say you have a molecule that has a nitro group and a ketone and you only want to reduce the ketone, you won't use Clemmensen reduction. If you want to reduce the nitro group and the ketone, you'll use Clemmensen reduction. If you just want to reduce the ketone and you don't want to reduce the nitro group, you'll use Wolff-Kishner. So, at the bottom here we talk about two ways to do the same reaction, because sometimes we have other functional groups in the molecule that will be affected by those reagents, and we've got to be careful about that. So if you'll notice, Wolff-Kishner is acidic. Conditions. And this is basic conditions. So if you have functional groups in your molecule that are sensitive to acid, you would want to use the Wolff-Kishner. If you have other functional groups that are sensitive to base, you would use Clemmensen. So that's why we have two different things here. All right, so that's on the top of the next page. Acidic. Conditions, and Wolff-Kishner is basic. So more and more we're getting into molecules that have more than one functional group, and when you have more than one, you've got to consider all the functional groups and their potential reactivity. Questions? Anybody? So that's 4 new reactions plus electrophilic aromatic substitution in chapter 18. Yeah? Carboxylic acid and aldehyde with which one? If it was an aldehyde, yes, they would both get reduced. Yep. All right. We're going to skip nucleophilic aromatic substitution, okay? We'll come back to this. In my class, we'll do it in chapter 25. So we're going to skip this. It's a sad day. Kind of a cool reaction. I think you'd like it, but we don't have time for it. So I'm sorry, you're going to have to wait until next quarter. Okay. So that takes us directly to synthetic applications of electrophilic aromatic substitution. We don't have time. I've already made the decision. I made a command decision here, and I'm going to change it. We'll stop early if we end up early. All right, one of the first things you need to keep in mind when you're doing electrophilic aromatic substitution and you're putting on more than one group on the benzene ring, the order is critical. If you do the right steps but they're in the wrong order, you'll get the wrong compound and you don't get partial credit. Okay, so you have to think about the order when you're putting things on a benzene ring. So, for example, this compound right here. One of these groups that we're starting from benzene, so if we put the nitro group on first, what would then we want to put this group on, what's the problem with that? Two problems. Nitro is meta-directing. It's not going to go on in the meta position. Number two, how are you going to get it on? Because Friedel-Crafts doesn't work with nitro substituted benzene rings. So Friedel-Crafts doesn't work with deactivated meta-directors. Friedel-Crafts doesn't work. So can't put the nitro group on first, have to put this group on first. So we can use, well, here's the good synthesis. And sadly, the wrong order is going to give you no points because you're not making the compound. We talked about some other ways to put a terp-butyl group on. I'm just going to use the Friedel-Crafts with the AlCl3. What do we want to do to ensure that this reaction goes pretty cleanly? What do we want to do here? Yeah, large excesses of benzene. Okay, so then we're going to put the terp-butyl group on. Then we're going to nitrate. Are we going to get any ortho at all? Yeah, I wouldn't even consider it. So I'm going to assume we're going to get all. Bulky, so mainly para. And then let's write the bad synthesis here. And really this aromatic chemistry, it's not as difficult as the synthesis that you've already done earlier in this quarter. These are not as hard. Students tend to do better on the test with this kind of stuff. So that's good news for you. And then if you try to do this second, no reaction. So reaction fails. Why? No Friedel-Crafts. No Friedel-Crafts on deactivated meta-directing rings. Now some students take this to mean that there's no any reactions on deactivated rings. That's not true. There's no Friedel-Crafts on deactivated meta-directing rings. They do all the other reactions just fine. Questions on that synthesis? Anybody? Yes?
Is it necessary on the excess?
I think it's a good idea. You might get a point off if you don't. Okay, so that just shows that you recognize that you're going to get over-alkylation. Okay. So the last example, we just put the groups directly on the ring and they were what they wanted. We may have to do functional group manipulation if we have things that are more complicated. So, for example, let's say we wanted to make this compound. So We certainly can't put the nitro group on first or we'll never get this group on. And if we try to use Friedel-Crafts to put this group on, are we going to get that as our major product? No, it's going to rearrange. So here's the trick way to do this one. Here's the good synthesis. Rather than Friedel-Crafts alkylation, we're going to do Friedel-Crafts acylation. And that's going to do great things for us because we've got our alkyl group on there. We're going to be able to convert this into we've got our acyl group on there. We're going to be able to convert this into an alkyl group by doing which reactions? The ones we just talked about. Clemmensen reduction, Wolff-Kishner reduction. We can turn that into the group we want and we won't get any rearrangement. Friedel-Crafts acylation doesn't give rearrangements. Friedel-Crafts alkylation does. The timing here is important. So this is the good first step. Do we want to get rid of this carbonyl? Do we want to do it first or we want to put the nitro group on first? Nitro group on first, because if we get rid of this first, then now that's an orthopara director. And the nitro group's not going to go on where it went. Aren't these fun? I really like, you guys like this better because you do really well on these. Okay. So we're going to make this. It's going on the meta position. Now we're going to get rid of that carbonyl. What reagent do we want to pick for that? Don't do Clemmensen. You see how this question here just brings up a lot of stuff. You don't want to use the Clemmensen. The Clemmensen will reduce the nitro and the carbonyl. We don't want the nitro and the carbonyl reduced. If we did, we'd use Clemmensen, but we have to use Wolff-Kishner. So what's Wolff-Kishner? NH2, NH2, and sodium hydroxide, not zinc-mercury amalgam, and HCl. This will also reduce nitro group. The other thing that's nice about these things that we're doing with electrophilic aromatic substitution is we don't really have to worry so much about stereochemistry with a lot of these syntheses. All right, so bad's the good synthesis. The bad, can't put nitro on first. Because our Friedel-Crafts won't work. Can't put propyl on directly. Why? Will rearrange. Number two, it's a activating group. So it's an orthopara director. So really a lot of things in this synthesis. So you got to know what you're doing here. Got to be thinking about what you're doing. So isolated steps won't get you anything if your steps are not leading to the correct product. Okay? Questions on that one? Anybody? All right. Sulfonyl group can be used as a blocking or directing group, which can be easily removed once it has served its purpose. All right, so we can put this group on benzene. We don't want to put the nitro group on first, just like the other two. We can put this group on, and that's already rearranged, so that can go directly on. But it's an ortho-para director. Ortho is your minor product because it's kind of bulky, right? And if we want this to be our major product, so maybe we'd get 20% nitro here, maybe, and then 80% in the para position. So our major product's going to come from the para because this is bulky. So another thing that we could do instead is block the para position with the sulfonyl group. And so this is what it looks like. Well, first of all, we'll say what we don't want, and then we'll do that. If we take this and AlCl3, and we use excess benzene to avoid overalkylation, we can make this, and that's good. But we probably, in the next step, HNO3, H2SO4 are going to get para as our major. And that's because this is sterically hindered. All right, so if we want to increase our yield, we're going to sulfonate. This should be our major product. That doesn't mean we won't get any in the ortho position, but we'll get a minor amount in the ortho position for two reasons. This isopropyl group is hindered, and the sulfonyl group is also, that sulfur is pretty large. So we're going to get this as our major. If we get that as our major product, we would have to separate, if we get any ortho, which we probably will, we'd have to separate that first. But this is our major product. This guy right here is ortho-para directing. This is meta-directing, right? And the good news is they both agree on where the next substituent should go. So then we nitrate at this point. HNO3, H2SO4. Here's our sulfonyl group. And this will be right here. Ortho to the ortho-para director, and meta to the meta director. So both agree on where that should go. And now we're done here. We're ready. We're going to use dilute H2SO4. and heat. That will take that off. Everything else will stay on, and that's our major product now. Pretty handy thing to be able to do. Now, let me ask you this. If this was if we were going to be doing a Friedel Crafts instead of a nitration, would that work? Yeah, Friedel Crafts. For Friedel Crafts, if you have this is a strong deactivating. If this was a strong activating, you could do Friedel Crafts. If you have a strong activating and a strong deactivating, you can do Friedel Crafts. This is weak activating, strong deactivating, so you wouldn't be able to do Friedel Crafts in a second step here. Okay, so I just wanted to point that out. All right, to add multiple groups to use more nitric acid H2SO4 and increase temperature, why is extra heat needed? Each nitro group added deactivates the ring. Therefore, if you want to add more than one, you have to use increased temperature. So when we do nitrations, we're very careful. We do it in my lab. We use we cool everything down in an ice bath before we do the nitration, to make sure that that solution doesn't get so hot that more than one nitro group will go on. Why wouldn't we want more than one nitro group on? Well, let me just give you an example here. If you heated this up rather than did this in an ice bath, if you let the temperature get away from you here, this is what you would make. What is that compound? TNT, right? Trinitrotoluene. So now you know how to make TNT. You can impress all your friends. All right. See that we had time for nucleophilic aromatic substitution. Okay, too late. No going back. I'm a little sad about that. Okay. You got enough on your plate. One less reaction is going to be to your advantage. Okay. Consider multiple pathways where more complicated syntheses are desired. All right, so let's make a little plan for this molecule. We're starting from benzene. We certainly, this is an alkyl group. We certainly do not want to put this on first or that on first, or we'll never get that alkyl group on, correct? So does everybody agree we need to put this group on first? So, and how are we going to do that so we don't get rearrangement? We're going to, if we want rearrangement, we have to acylate and then use Wolff-Kishner or Clemmensen. This will rearrange like a shot. And the groups, if you put that on first, this is in the ortho position, this is in the para position, this is an ortho-para director. So that's a great plan for us. So that's the plan here, and then we'll talk about the rest. First, put on this group here. It is an ortho-para director. So now you can put on the other groups in the correct position. And we're going to have to do that 2 steps. We're going to acylate, and then we're going to get rid of the acyl group, the carbonyl group first. All right, so now once that's on, what goes on next? Once this group is on, and we have 1, 2, 3, 4, butyl benzene, what goes on next? That has to go on next. That absolutely has to go on next, because if you put the nitro group on first, this is going to go on with Friedel-Crafts. It won't work. Okay, this would have to be a strong activating group with a nitro group to work with Friedel-Crafts. This is weak activating. So we absolutely have to put that group on second. Order matters here. So we're going to put on the acyl group next. Can't put on the nitro group. Because there's no Friedel-Crafts with a nitro group on the ring. Unless there was an strongly activating to cancel it out, you will not get Friedel-Crafts. All right, and so then the third step, of course, is going to put the nitro group on. All right, so we've got the plan. Let's write out our synthesis in the forward direction. Starting with benzene, we're going to acylate. This is so we don't get rearrangement. Count your carbons here. That's 1, 2, 3, 4. It's a 4-carbon chain that we want to put on. In the second step, I'm going to just use Clemmensen reduction. Okay, so far so good. 1, 2, 3, I need one more carbon. Then I'm going to acylate. Every one of these steps has to be carefully timed. We're going to get that. We will get ortho, nothing you can do about it. They usually go together unless you have a really sterically hindered group. So you will get some ortho there, there's nothing you can do about it. That just goes along with aromatic chemistry. And then HNO3, H2SO4. So the good news here is that we have this is an ortho-para director, and this is a meta director. So the nice thing is they both agree on where that nitro group should go. So a pretty complicated synthesis that we can do with everything that we've learned in this chapter. But that's the last page. We'll stop right there, and we're done. I'll see you in the review at 3. Thank you. Thank you. Thank you.